Okay, welcome to 2.4, Getting Down to Business, and this is a solidifying understanding task. So here's the situation. Calcurama had a net income of $5 million in 2002. So let's document that. Okay, we're going to start modeling already. All right, so we have this company, Calcurama. All right, and in the year 2010, they had a net income of $5 million. So instead of starting with 5 million, because these numbers are going to be really big, I'm going to say my numbers are in millions of dollars. So income in millions. So instead of putting 5 million right here, I'm just going to put a 5. Okay. Now, there's another company, while a small competing company, ComputerFest, had a net income of $2 million in 2010. So here's ComputerFest and their income in millions again. So I'm just going to put a 2 right here. Now think about this. You have the opportunity to invest in one of these companies right now. All right. And you look at their net income in 2010, Calcurama, 5 million, ComputerFest, 2 million. Who do you think you might invest in right now? Well, let's keep reading. The management of Calcurama develops a business plan for future growth that projects an increase in net income of 0.5 million per year. All right, so let's think about our pattern of change in this sequence then. All right, if I am increasing by 0.5 million per year, that means that the pattern of change here will be a common difference. D equals, and what does D equal? 0.5. Income in millions. So that means in 2011 we have 5.5 million. In 2012, 6 million. In 2013, 6.5 million. In 2014, 7 million. In 2015, 7.5 million, and so on. So we like the direction this company is going. All right, that's a linear growth right there. Okay, so what's ComputerFest's plan? While the management of ComputerFest develops a plan aimed at increasing its net income by 15% each year. 15% each year. All right, so what would the pattern of change be there then? Well, if I'm increasing by 1%, all right, that means I'm going to multiply by a decimal, all right? And that means I won't have a common difference like Calcurama has. I'm going to have a common ratio. And what is my common ratio going to be? Be careful here, all right? We're increasing by 15% each year. And 15% as a decimal is 0.15. But remember, we also need to represent 100% of the money we had the previous year. That means the common ratio would be 1.15. That is how we represent an increase of 15% per year as a decimal. 100% plus 15% more, 1.15. Now, I'm going to get out my calculator. And I have a fancy calculator that I can create a table and it will round my answers to 4 decimal places. So when you punch these out, if you have something beyond 4 decimal places, just round it to the 4th decimal place. So if I take 2 and I multiply by 1.15, I am going to get 2.3. Okay, and then in 2012, 2.3 times 1.15, and I get 2.645. And then in the next year, 2.645 times 1.15, and I get 3.0418. And my calculator may have rounded to that 8 right there. Okay, and then the next year, I'm going to take my 3.0418 and multiply it by 1.15, and I get 3.498. And then let's do one more year. So 3.498 times 1.15, and I get 4.0227. Now let's think about this. Which company are you going to invest in? All right, the linear growth with a common difference of 0.5, or the exponential growth with the common ratio of 1.15? Wow, a lot to think about there. So, Part A, create standard mathematical models, and we've done that with two sequences right now, but they want like table, graph, and equations for the projected net income over time for both companies. Attend to precision and be sure that each model is accurate and labeled properly so that it represents the situation. All right, well, we've done a really good job with these sequences right here. But you know what we're going to do? We're going to go to our modeling data frame and we'll do a table, a graph, and recursive and explicit equations. And then we're also going to talk about what that stuff means. Okay, so let's go ahead and model the data for Calculama right here. And we started with our sequence. We're not going to do a diagram for that, but we will go now right to our table. And very important, you need to think about right now, based upon the context of this problem, are you going to start with an x equals 0 or a 1? Now, wasn't it the year 2010 when Calculama had a net income of $5 million? So typically, a problem like this, we're going to call the year 2010 year 0. So I'm going to start with an x equals 0. And then I'll just increase my x's by 1s, just like we showed on our sequence on the previous slide. So let's go 1, 2, 3, 4, and hopefully we see the pattern, and so on. And that will represent every x, or every year 2010 and beyond. All right. Now, f of x then is my outputs, and I can see several of them right here in my sequence. So f of 0 is 5. F of 1 is 5.5, f of 2 is 6, f of 3 is 6.5, f of 4 is 7, and so on. And I'm going to come up with an expression for all of these f of x's in just a moment. Some of you could do that right now, I hope, but we'll do it when we get our explicit formula over here. So let's talk about our pattern of change. Didn't we see a common difference of 0.5? Common difference 1/2 or 0.5 if you'd like it. Now, I am hoping we're to the point where we know what that means. So, what we're going to do then is take a look. Common difference of 1/2. That means the sequence is, so this sequence with a common difference must be arithmetic. The function will be, well, if I create a function based on an arithmetic sequence, then my function will be linear. So that means the data will show a pattern of linear, and because my common difference is a positive number, that would be linear growth. Oh, beautiful. All right, let's set up our graph. So on the horizontal axis x, I'm going to do my typical 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's far enough. Now, I look at my outputs and they're not getting that big that quick, so I would probably go same thing, 1, 2. But I also know that ComputerFest has a common ratio, and so I think those numbers might get larger down the road. So I think I'm going to double up here because I want to put both graphs together on the same graph eventually here. So I'm going to go 1 and then a 2. Yeah, 3, 4, 6, 8, 10, 12, 14, 16, and 18. Beautiful. So let's go ahead and graph these points right here. All right. And again, plot your first one. Your y-intercept would be when x is 0, f of 0 is 5. So 0, let's go up to 5. And now, every year you're just going to go up by a half more. So, I mean, you could do that slope pretty easily, okay? Rise 1 and run 2. All right, but that would take me all the way to there if I do that, so I better do this. Let's go 1, and f of 1 is 5.5, so that's just going to be right there. Okay? f of 2 is 6, and that's going to be right there. F of 3 is 6.5, right there. And f of 4 is 7, right there. Now, let's start thinking about, do we think this data, is it more appropriate to think of it as continuous or discrete? I mean, the way I see it right now, you know, in a sequence, a table, that looks discrete, but think about the problem here. This is the net income of a company, and that's changing continuously as the market changes. All right, so I think I'm going to call this continuous, so I'm going to do a solid ray through these points with an arrow at the end, just like that. Continuous. Okay, and we'll get to that part down here in just a moment. Okay, now next, our formula. Well, for the formula now, we have a common difference, which means we're linear, and our first x is a 0, so that means I can use my slope-intercept, m times my x, and if that first x were a 1, that x would be quantity x minus 1, but it's a 0, so that's just m times x plus my y-intercept b. Alright, so let's fill that out. So f of x equals, and you guys now know that the common difference is the same thing as the slope, okay, 1/2 x plus my y-intercept, and I can see the y-intercept in my table, it is 5. I can also see it pretty clearly on my graph right there, 5 plus 5. Now the recursive formula. Oh, let's put the 1/2 x plus 5 right there. All right, and then we've got f of, now remember your recursive formula, this is function notation of your first ordered pair in the table right there, which is 0, 5. So the x is 0, f of 0, and what does f of 0 equal? It equals 5. Right on. And then the recursion equation, f of x equals f of, and what always goes here, f of x minus 1. This represents the previous term. What do we do to the previous term to always get the next term? Well, what did we do? Our pattern of change. We added 0.5, or plus 1/2. Plus 1/2, there it is. Okay, now let's get back to the end over here. Let's talk about continuous or discrete, and we decided we would represent this with a continuous function. So f is a continuous function with a domain of, now with a continuous function, we use interval notation. So x is in, and notice I did a bracket on the left because we represented the year 2010 with a 0. That's my first input, and x can equal that 0. And this is going on and on and on and on for as long as this company exists. So we don't know how long that's going to be, so we're just going to go towards infinity, and because we can never reach infinity, we have to put a parenthesis right there. Okay, there's our models. Let's use these to answer questions. Thank you. Okay, so let's go ahead and model the data for the company ComputerFest. And here's the sequence we already created. We won't need a diagram here. And now let's think again. My first x right here is going to be the year 2010, which we will call year 0. So we're going to start with a 0 again and go by 1 year intervals. So there's all my x's. And then my f of x's would be the outputs of my sequence over here. So I'm going to go a 2, a 2.3, a 2.645, a 3.0418, and then a 3.498, and that's far enough to see the pattern. We'll come up with our explicit expression in just a second. And now let's talk about what do we know. Now remember, ComputerFest didn't have a pattern of change that was a common difference, it was a common ratio. We were multiplying by 1.15 every time to get these numbers. So what does r equals 1.15 really mean? Well, if I have a common ratio, I know that the sequence is geometric. I know then the function will be exponential, And so then I know the data will show a pattern of exponential. And because my common ratio is greater than 1, that's going to be exponential growth. And we will see that in just a moment. In fact, let's go ahead and graph right now so we see it immediately. And I was going to put both graphs together here, so I'm going to scale my x-axis and my f of x axis exactly the same. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here, I'm going to double up things, so I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, and that should be good. And let's hope I need this with my company ComputerFest that is using a common ratio. Okay, so let's plot our points then. The y-intercept when x is 0, f of 0 is 2. Okay, and then f of 1 is 2.3. Now these are going to be a little more challenging, so just be careful, do your best. They do not have to be perfect. F of 2 is 2.645. So there's 3, so 2.645, about right there. F of 3 would be a little over 3, about right in there. Okay, and f of 4 would be almost 3.5, almost 3.5, so that's about right in there. And again, these aren't perfect, but they're close. I think this one needed to be a little bit off, but I can't change it now. And now I want to go a little bit farther here. So I'm going to get out my calculator because I want to see the concavity of this exponential growth. Well, I already have the next one because it's in my sequence. Okay, f of 5 would be a little bit more than 4. Here's my 5, and I'm going to go a little bit more than 4. Okay, that's not bad. Now, breaking out my calculator, let's take that 4.0227. Come on, calculator. All right, there it is. I'm up now. All right, so I'm going to go 4.0227 times my common ratio of 1.15. And that's going to be, and I'm rounding to the 4 decimal places, so I see a 4.6261. So f of 6 is 4.6261. There's 5, so it'd be right in there. Okay, and then take that and multiply it by 1.15 times 1.15, and I get 5.3200 or 5.32. So at 7, I'm going to go up to, there's my 5.3, be about right in there. Okay, and then take that and multiply it by 1.15, and I'm at 6.1180. 6.1180. So there's 6, so a little bit beyond that 6 right in here. Okay, times 1.15, and I'm a little above 7. I'm at 7.0357. So 7.0357. So there's 7, a little bit above that. I lost my arrow, there it is. So I'm right in here. All right, let's do one more. So times 1.15, and now I'm at 8.0911. So a little above the 8. Right in there. Okay, I know that was kind of tedious, but again, I really wanted to see my concavity, and I know that scatter plot's not perfect, but can you see clearly now that this is concave up? Which if I kept going and going and going, I would get that exponential growth pattern. And again, like the last problem, you know, year 0 is 2010. The years are increasing continuously, and so is my data over here. As people are investing in this company, ComputerFest, the net income is going up and up and up. So I'm going to call that continuous like that. And this is ComputerFest right here. And I promised you we'd put Calculama on the same graph so we could kind of compare the graphs. So there's Calculama right there. Okay. Oh, how cool. All right, so let's finish our formulas here. So an explicit formula. Well, ComputerFest is exponential. We said that up there, and our first x is a 0. So we're going to go a times b, and again, that first x is a 0, so that's going to be to the x power equals. Now, if we know what the a and the b are, we're set. Now, isn't a nothing more than our first output, 2? And isn't b nothing more than our common ratio, 1.15? So there is my explicit function right there. F of x equals 2 times 1.15 to the x power. Let's put that right here. Okay, now the recursive formula. F of blank equals blank. Look at the first point. My x is 0. F of 0. And what does f of 0 equal? 2. And then f of x equals f of x minus 1. And what's my pattern of change? What did we do every time? We multiplied by 1.15. Finally, f is, we already decided this would be a continuous function. And again, I'm starting at year 0 and I'm going to infinity. So I'm going to do the same interval notation, 0 to infinity. Great job. Okay, part B, compare the two companies. How are the representations for the net income of the two companies similar? How do they differ? What relationships are highlighted in each representation? That's a pretty deep question. I think we can talk about the similarities and the differences if we just look at our original sequences right here. Excuse me. So, what is similar about this data? Well, let's think about this a second. 5, 5.5, 6, 6.5, 7, 7.5. This data is increasing, and so is the data for the net income of ComputerFest. They are both increasing functions. Okay. Next, didn't we decide this is an investment? This is the net income of a company, and that is changing continuously in both of these models. So we decided we were going to call both models continuous. All right. And they both also started in the year 2010, which we called year 0, and then they're going on and on and on and on. So we gave these both the same domain. X is in the half close interval from 0 to infinity. So the domains are the same. Now, what are the differences? Well, I think we can see this just by looking right here at our sequences again. All right. Well, Calculama, the pattern of change was a common difference. In ComputerFest, the pattern of change was a common ratio. In Calculama, we added 0.5 every time. In ComputerFest, we are multiplying every time by 1.15. So the differences would be common difference versus common ratio. And now that can give me some other differences too. If I have a common difference, isn't the sequence arithmetic? And if I have a common ratio, isn't the sequence going to be geometric? So we are arithmetic versus geometric. And that means the functions are, well, an arithmetic sequence leads to a linear function, and a geometric sequence leads to an exponential function. So linear versus exponential. Beautiful. Now, what relationships are highlighted in each representation? So I'm going to go back to the models, and I'm sorry, but with this hyperlink, all right, nothing's showing, so I've got to get everything back up there real quick for us. Give me just a second. Wow, I wish I could do the math this fast. Almost there, almost there. There we go. That's everything right here. So now, Calculama, we have a common difference. Where do we see that in each model? Well, in the sequence, you can see the terms are increasing by 0.5. In the table, we can see our outputs f of x are increasing by 0.5. All right. In the graph, we can see a slope of 1 over 2. Now, watch when I do this. I go from 4.5 here. Let's go to whole numbers here. Where's the whole number? There I'm at 6. And so if I go up 1, I'll go up to 7. And then I'm going over 2 to get to that point. So I see a slope of 1 over 2. I see that common difference of 1/2 right there, the slope of this line. All right. I see the slope in my explicit function is my m, so there's the 1/2 right there. All right. And I see the slope in my recursive formula right here. My pattern of change is plus 1/2. So I see that common difference. It's the core to every model, the sequence, the table, the graph, the explicit, and the recursive formulas. How cool. Now, yeah, that's important stuff right there. ComputerFest. So I've got to click through really quick again. Let's get all this up again. You guys have it already. Give me just a second. Oh, there we go. Exponential growth. Okay, so ComputerFest has a common ratio. Where do I see it? Well, in the sequence, the pattern of change, we multiplied by 1.15 every time. The outputs of the table, the pattern of change, we're multiplying by 1.15 every time. In the graph, I see the concavity. I see the exponential curve. That is because we have a common ratio of 1.15, and it's exponential growth because that common ratio is bigger than 1. In the explicit formula, I see 2 times a base of 1.15. That's my common ratio right there to the x power. And in the recursive formula, I see to get the term I'm looking for, I take the previous term, and what do? I multiply by 1.15 every time. Common ratio. It is in every model. It's the core to every model. Okay, part C. If both companies were able to meet their net income growth goals, which company would you choose to invest in and why? So let's look at the graph where we put both functions on the same graph. Now, let's make a decision. Are we going to invest in Calcurama, whose net income is showing linear growth? So this data would just continue to do this. Or are we going to invest in the company that is showing exponential growth? So this data has some concavity to it, and it's going to eventually do something like this and just keep going and going, but then it's going to go up and up and up like that. Now, do you agree we would like exponential growth rather than linear growth? So I would invest in that smaller company, ComputerFest, because just in a few more years, ComputerFest is going to have a net income that is equal to and then greater than Calcurama. So I would invest in a company whose net income is growing exponentially. Exponential growth always will overtake linear growth in a very short time too. Okay, D. When, if ever, would your projections suggest that the two companies have the same net income? Well, if I go back, they're getting pretty close right now. All right, this is year 10. All right, right there, and they're getting closer and closer and closer. So let's think about this. What would be the easiest way to figure out in exactly which year they would eventually have the same net income? Can we just take our table and expand it? So this is the table we started with, and now I used an F for Calcurama and a G for ComputerFest, so I can differentiate between the two. So X is my number of years beyond 2010. F of X, Calculorama, and this measures net income in millions of dollars, and G of X is ComputerFest, which measures net income in millions of dollars. And the question is, will we ever eventually get to the same number at some point during a year? So let's expand our years. 5, 6, 7, 8, 9, 10, 11, 12, 13. See, this is just beyond where our graph was right there. And now, Calculorama is easy. The outputs were just a common difference of 0.5. So let's go 7.5, 8, 8.5, 9, 9.5, 10, 10.5, 11, 11.5. Now, ComputerFest, because of a common ratio, we have to get out our calculator again. And I'm going to go ahead and round to 4 decimal places if I have to. All right. So let's take the 3.498. And I know we did this earlier, but I didn't document these exact numbers. I just plotted them on a graph. Now we need the numbers for our calculator. So let's go 3.498 times 1.15. And I get 4.0227. Okay, times 1.15, and I get to 4 decimal places 4.6261. All right, and then times 1.15, and 4 decimal places, I am going to get 5.3200. I probably just put 5.32. I did. And then times 1.15. This is tedious, but be careful. You can do it. And I'm getting 6.1180. So I probably just said 6.118 times 1.15. And that's going to be 7.0357 times 1.15. And that's going to be 8.0911. We're getting closer. Year 11 times 1.15. And I have 9.30047. 48. Oh, my calculator rounded a little differently than I did. But I'll go with the 48 there. That's fine. Times 1.15. And I am getting 10.701. And then times 1.15 again. And I'm getting 12.306. Okay, awesome. Now, do you see what I see? At year 12, okay, Calculorama has a net income of $11 million. And ComputerFest has a net income of 10.701. But then during that 12th year, at some point, well, at year 13, Calculorama's at 11.5 million net income. But now look at ComputerFest, 12.306. So that means sometime during year 12, ComputerFest and Calculorama have the same net income because they're continuous. So Calculorama and ComputerFest will have the same net income in millions of dollars at some time in, and what year is that? Well, remember, year 0 was 2010, so that would make year 12 2022. At some time in the year 2022, Calculorama and ComputerFest will have exactly the same net income. All right, good. How did you find this? Well, what did we do? We expanded our table. I found this by expanding my table. Will they ever have the same net income again? Well, if Calculorama has a common difference, it's linear growth. ComputerFest has a common ratio, that's exponential growth. Let's look at the graphs again. So linear growth is just going to continue to go in this direction in a perfectly straight line. But exponential growth, ComputerFest is going to go and then go up and up and up and up and up like that. So again, beyond that day in 2022, when they have the same net income, after that moment in time, all right, the company that will have the greater net income will always be ComputerFest. So, one more time. Will they ever have the same net income again? No. Okay. Beyond the year 2022, ComputerFest will always have a greater net income. And that's why we wanted to invest in ComputerFest. Okay. Now, since we are creating the models for these companies, we can choose to have a discrete model or a continuous model. Now, we chose continuous. And even that very last question, will they ever have the same net income? Well, that was between year 12 and year 13. All right. And if we thought of this data as discrete, then they never would have had the same net income. But we're thinking of this as continuous. So I'm going to say, let me read it again. Since we are creating the models for these companies, we can choose to have a discrete model or a continuous model. What are the advantages or disadvantages of each type of model? So I'm going to go back to the graph, my continuous function, the solid lines right there. Okay, and I'm going to answer the question. IMO, in my opinion, continuous models give me a better visual of the data. I can see the linear growth much more clearly with this continuous graph. I can see the exponential growth much more clearly with this continuous graph. All right, and also, if that was discrete, again, those two companies would have never had the same net income. All right, so I think continuous is much more appropriate for this problem. And what are the advantages and disadvantages? Just the clarity of what I see, the visual. Okay, now I'm going to add one thing, because you guys are going to look at the Ready, Set, Go, and there's going to be some multiple choice questions where they're going to ask you for like what type of set of numbers are the possible inputs of some situation. All right, and so they're having you review what you did in middle school. All right, and what you have here is the set of real numbers. So all of these numbers you see in this Venn diagram are real numbers. All right, and within the set of real numbers, you have the set of natural numbers. Those are your counting numbers. And then the whole numbers would be 0 and all of the natural numbers. And then integers would contain your negatives as well. So -4, -3, -2, -1, and then 0, 1, 2, 3, 4, and so on. All right. Now there are symbols for all of these sets of numbers. And we've been working on our interval and set notation. So I want you to know what symbols represent certain numbers in interval notation or set notation. So the set of real numbers, that is any number. And that is x is in the open interval from -infinity to infinity. Any number is a real number. Now, that double bar R with a plus, that's the positive real numbers. So that is x is in, and you know what? I should have a greater than, yeah, and I do there. So that's 0 to infinity, but because of this parenthesis right here, x cannot equal 0. 0 is not a positive, and I have a parenthesis on this side because we can never reach infinity. Then the set of integers, that's the double bar z right there. And that's just all your integers. So this is set notation. This is -2, -1, 0, 1, 2, and so on in both directions. So we can go forever in both directions, to the left or to the right. Now the whole numbers, that's n in, and that's set notation 0, 1, 2, 3, and so on. And then the natural numbers, which are the positive whole numbers, or some people call those the counting numbers. So n is in the set, 1, 2, 3, and so on. So again, and let's think continuous and discrete. The set of real numbers is continuous. It's any number. The set of positive real numbers also continuous, but it's not as large of an interval. And then I get into discrete. The set of integers, that's a discrete set of numbers. It's only these numbers, nothing in between. The set of whole numbers is discrete. and the set of natural numbers is discrete. All right. Have this down because it will help you on a couple of your ready, set, go problems today. And you guys have a great day. Do your ready, set, go carefully, and let me know if you have any questions.